Welcome back. This is section 8.6, momentum vectors, and this is section 7.6 in your textbook. We looked at two objects that collide either head-on or one hitting directly from the back. So they're either going in the same direction or they're facing each other. But momenta is conserved even if two things strike each other at an angle. You can imagine two pool balls that are coming in at an angle to each other. Some of that direction, or some of that pool ball, if it's going in this direction, some of it's going directly north and some of it's going directly east. This guy who's about to hit it, if it's coming here, some of that is going directly west and some of it's going directly north. Well, what's going to happen when these two balls strike? So this ball is going to come up here and strike here, and this one is going to strike here. What's going to happen when they land? Well, you've got these two guys. This is going to cancel out this, so you're not going to have any more east-west direction. They're going to cancel if these are equal and opposite. But since they're both heading north, both these balls will strike and go north. So a collision doesn't have to be in two dimensions or in one dimension. It can be in two dimensions. In fact, you can even have, as long as you have three balls, you could have three dimensions to where, like if you have something exploding in the air, hitting each other at the same time, you could go in multiple directions, east, west, and the z, x, y, and z axis. So let's start with this example. We've got two cars, and they are one's going directly east and one of them's going directly north. What's going to happen to the momentum when those two cars crash? You've got a mass times the velocity in the red car, a mass and times the velocity in the orange car. They're going to strike, and as they strike, you're still going to have a mass and velocity. They're going to sum together. So anything that would be directly east-west would cancel, but there isn't anything. One's going due north, one's going due east, and so what'll happen is you'll end up at the end going in a northeasterly direction. So this is exactly backwards of the previous example. Instead of two things crashing together and making one momentum, you have a firecracker that's going in a certain direction, so it's going MV in this direction, so this is falling, and then it explodes, and when it explodes, these pieces are going to go in different directions. The different directions are going to equal the same momentum that it started with. You're not going to gain momentum by splitting up. So instead, here's the original momenta. Some of this is going to be in this direction, and some of it's going to be in this direction. If you remember the parallelogram rule, you can make a parallelogram to sum up the two components of the resultant. The resultant is what we started with here in this case, and it's going to split into these two parts. So we could actually determine what this angle is going to be. We could determine what this angle is going to be, and what the magnitude. So I know what the speed and the direction. So I could actually make some predictions. If you gave me enough information, I could make some prediction about exactly where these guys would fall. This is a cool picture. This is a bubble chamber. So this would be electrons and protons when they crash them into each other at very high speeds. And you're going to see essentially it looks like a big pool table. And if you crash them in at different angles, they're going to go away from each other at different angles. And you can add those angles up, and it would be the original momentum. Whatever the momentum of the initial one, the straight line one, or when you add up the angled, you can do this when you're playing pool. You strike a ball into other balls, and some will go left, some will go right, all at different angles. They add up to the original momentum of the ball that you started with. Now, we didn't do a lot of math in this. You can see that we would have to use sine and cosine to split these vectors up. But knowing that you can split them up into the vectors, especially like we did with the parallelogram rule, means that you have some basis that if I gave you some math to do, that we could probably tackle this. But what is true about the vector sum of momentums in a collision? The vector sum is going to be the same as the original momentum. The vectors add up in angle and in magnitude to the original momentum of the object before it split, or when two things crash, it adds the two moments together, and you end up with a new angle, depending on what the originals were.